Okay, so if all nuclei that we were studying in NMR were all independent and by themselves, they would all give exactly the same frequency, and so we wouldn't find any useful results. But it turns out that these nuclei are surrounded by other electrons or other elements that have electrons. And so when the molecule is in an external magnetic field, the other electrons also have little magnetic fields that they set up because they're spinning. And so they set up magnetic fields of their own. These local magnetic fields are going to be opposite to the applied field. And so the actual field felt by the nucleus is a little bit weaker than the applied field. So again, these electrons that are surrounding the nucleus in question actually shield the nucleus in question. And so the nucleus feels a little bit less of the applied magnetic field than it might otherwise if those other electrons weren't there. And so because this nucleus has a smaller magnetic field than what is actually applied, so that's what I said already, it's said to be shielded. And what happens is that it's going to need, the applied field is going to need to be a little bit higher to overcome and allow the spin to flip. So let's look at the example. A normal hydrogen nucleus may require 60 megahertz of frequency to flip, but because that nucleus is shielded, the applied field has to be a little bit higher to overcome. And so what happens is the signal shifts slightly to the right if it's shielded. If you look on this is the x-axis here where the signal is. And so we call going to the right upfield. We call going to the left downfield. Keep in mind that if you're going toward upfield, the carbons or the nuclei are more shielded, and the further to the left or downfield, the more unshielded a nucleus is. And so here's the equation. The field is equal to the applied field minus whatever local field is induced by the local electrons. So every single element, every single nuclei will be in a little bit of a different local, have different number of local electrons, and so the B local will be a little bit different every time, and so overall the different nuclei will end up in different locations along the x-axis. Okay, so again, shielding tends to shift the absorption to the right, which is called upfield. Shielding tends to happen, and this is probably the thing you need to know the most. Shielding happens when there's an increased electron density around the hydrogen or carbon. So things that tend to donate electrons, which we'll talk more about in a minute, but so carbons and hydrogens, things that donate electron density tend to be more shielding, and so those nuclei tend to be further to the right. Deshielding shifts the signal downfield to the left, and this happens when there's a decreased electron density around the H or C. That tends to happen when we have more electron withdrawing groups attached to the carbon. So oxygen, halogens, nitrogen tend to be more deshielding, and so you see those peaks toward the left. Now they get a little bit confusing because the left, which is more deshielding or less shielding, has the higher ppm. All right, so here you can sort of see the x-axis. So a proton, which is just be a hydrogen atom that's all by itself, may be way over here, but well, that's just a proton without the electrons at all. The proton over here on the left. Here's a hydrogen atom. which has very little shielding. But now hydrogen in a molecule tends to be more shielded. And you can see here that these are mostly inorganic compounds that you're seeing here. Hydrogen with the oxygen is more shielded than 3 chlorines. But hydrogen is more shielding. Sorry, hydrogen, the carbon is more shielding than the oxygen, so it's further to the right. And anyway, what you see, this dotted area, that tends to be the region where most of our organic hydrogens can be found. This is not a critical picture here. The ones that'll come in a little while will be a little more critical. So here, this is a little bit more important and probably a more helpful picture for you. This shows you the region of the spectrum, the ppm line that shows the organic hydrogen nuclei. So if you remember early on in the previous slideshow, I talked about tetramethylsilane, which is a silicon atom with 4 methyl groups attached. And these tend to be a good 0 point. They kind of mark the end of this area. And so these hydrogen all absorb right at 0 ppm. If carbon's in the center, just slightly to the left. So most sp3 carbons are pretty highly shielded, and they tend to be in this region, somewhere around 1 or 2. So you can see here, here's all sp3 hybridized carbon. These are all sp3 hybridized carbon. So our single bonded carbons tend to be in this region. Now look here, we've included a C double bond O. Now notice that the C double bond O isn't on the carbon that has the hydrogen yet. So it's like a neighbor is very electron withdrawing. So these kind of hydrogen, if they're near a carbonyl group, tend to be a little higher because that means they're more de-shielded. The electronegativity pulls electron density away, and so these are a little bit lower. Same thing here. Now here, the carbon where the hydrogens are attached are directly attached to an O, which is an electron withdrawing element. So these hydrogen are even at a higher number, which is more de-shielded. Here's a nitro group, which is very de-shielding. And so you can see here that the hydrogen in red, the hydrogen are even further de-shielded. Here's the hydrogen on a carbon that's also got some chlorine, so halogens are also very de-shielding. You don't need to memorize these numbers, but just kind of recognizing the shifting and what, the more de-shielding we have. So here we have the halogens and a double bond. Double bonds can also be de-shielding because there's fewer hydrogen. And they're pulling the electron density away from the hydrogen. So we're getting higher and higher ppm. Benzene rings are pretty de-shielding, and we'll talk a little bit more about them because they've got all these double bonds, and so they're pulling electron density away from the hydrogen. Benzene rings tend to have hydrogens in around 7. And then you can see here a hydrogen directly attached to a carbonyl group has a pretty high. And there's actually probably a few that might be even a little higher, but you get the idea. The more electronegative elements, the further to the left you're going to be. And a lot of it's relative at this point. All right, so again, this is just kind of given similar to what that last one is, kind of dividing the spectrum into its region. So like I said, saturated carbon, hydrogens with saturated carbons tend to be around 1 to 1.5. Allylic, which means the hydrogen is near, not on a carbon that's double bonded, but near a carbon that's double bonded. And it could be CC double bond, or it could be a CO double bond, or a CN, or whatever. But a hydrogen next to one away from a double bond, that tends to be about 1.5 to 2.5. If the hydrogen that the carbon is attached to is also attached to an O or an N or a halogen, that tends to be in this region. If you've got double bonds, They tend to be in this region, and of course it'll be further left if it's double bonds and oxygen, halogen, etc. And then the aromatic tends to be in this region. The aldehyde was what we saw. That tends to be up here. But this is sort of a helpful range. And I've also got some documents on Canvas that you can use to get a little bit more precise than this. All right, so if we look at this spectrum, and remember what I said earlier, we have to look at every peak in an NMR spectrum. We don't ignore any the way we did in mass spec or IR. So if we want to kind of get an idea about which peak is which, at this point, we're kind of all relative, but remember I said that benzene ring hydrogens tend to be around 7 or 8. So these happen to be the hydrogen. There's 1, 2, 3, 4, 5 hydrogen that are attached to the benzene ring, and those are represented by this peak. Now you might say, okay, here's these two peaks. Which one's more likely to be the one further left? Well, notice this is a hydrogen on a carbon attached to an oxygen, so that's going to be in this region. It's probably even a little further left than we might expect it to be. This carbon's also attached to a benzene ring, so both the benzene ring and the oxygen are electron withdrawing, and so these hydrogens are more deshielded, so they're further left. And then these hydrogens attached to this carbon here on the green arrow are the furthest to the right because they're sp3 hybridized. Now they're not quite as far. They might, if it wasn't for the C double bond O, they might be even further, closer to 1, but they're around 2 because they're near the C double bond O. So that's one example, and we'll be looking at some other examples. It's an interesting topic. All right, so this actually just describes what I said in the last slide. So in benzyl acetate, there's the 3 different hydrogen. The benzene is around 7 to 8. The hydrogens next to the benzene ring, the hydrogen on the carbon next to the benzene ring are less shielded, but because of the benzene ring and because of the oxygen, and then the most shielded is the methyl group all the way down on the right-hand side. All right, so here's another example. This is 1,2,2-trichloropropane. So notice that we have 2 peaks. One peak has to do with these 3 hydrogen, and then there's 2 hydrogen over here. These 2 are a little bit more deshielded or unshielded because they have this chlorine attached directly to the same carbon that the hydrogens are attached to. These 3 hydrogens are all attached to the same carbon, and they're a little bit deshielded, so they're a little bit further to the left than they might normally be because of the chlorine, but these are even further over to the left because the chlorine's directly attached to the carbon. And we'll talk about this in a little while too, but one thing that's also true, and this one I think you can see, this peak is about 2/3 of this peak, and so the ratio of the peak will be equal to the number of hydrogen. Now you can't always tell that, and sometimes you'll see a little number written to it, and that tells you how many hydrogen are represented by that particular peak, and that can be very helpful. So sometimes, and it's technically the area under the curve, and this looks like a straight line, so it's pretty easy to see that that's 2 and that's 3, but you can't always tell. So a lot of times that information will be given to you. And again, this slide just tells what I just said. So the hydrogens on C1 are more electronegative because of the chlorine. And so those have less shielding and they're further to the left. The hydrogens on carbon 3, which is the one furthest to the right, have no chlorines on the carbon themselves, so shielding is greater and so it's more upfield. You can pause this and read this if you want to, but it's pretty much what I just said on the previous slide. All right, let's identify the peaks on p-xylene. So what we expect, let's see, we've actually got, so this, let's just look at this formula. It is C8, it's hard to tell, C8H, H10. And so we have the CH3 groups, and you can see due to symmetry that they're going to be the same. And then we have 4, let's change the color here. We have 4 hydrogen right here, and they're all symmetrical, so they're all going to be the same. So we've got 2 peaks, and we can see that there's 2 types of hydrogen, so that makes sense. And hopefully you can see that we talked about benzene hydrogen being around 7. So these 4 are represented by this peak. Go back to the green, and these green ones over here are represented by this peak. You might be wondering what this green line here is. That's actually an integrator, and so what it's doing is it's figuring out how much area is under the curve. And so one thing you can do is you can measure this distance. I'm going to get a different color so you can see. Measure this distance. That represents the area under this curve. You can actually physically take a ruler and measure that distance. And then you can measure the distance here. This is kind of old school. Pretty much you'll be given a ratio. But you can literally do that, is measure the ruler and then compare the two. Divide the bigger one by the smaller one, and you get the ratio. So it turns out if you were to do that, you can kind of maybe estimate it. This again is about 2 to 3, and that makes sense. So 2 to 3 is the same as 4 to 6. And so that makes sense. The ratio, there's three hydrogen under this peak and 4 under this peak, the ratio being 2 to 3. And like I said, sometimes you might see the 2 written there and the 3 written there. But keep in mind that those are ratios and not necessarily whole numbers. So sometimes in this case, because there's 10 hydrogen, you've got 4 and 6. So those are just some things to keep in mind. All right, so this again is just talking about what I just said. So these hydrogen are more de-shielded because they're on the benzene ring, so they're down here around 7. The sp3 hybridized carbons over here, the hydrogen on these carbons are much more shielded, and so they're much more upfield. They're not quite as far over as 1 because they are directly attached to the benzene ring. All right, and here I'll just repeat myself again what I said. The peaks are proportional to their number of hydrogen present, like I said. So it technically is the area under the curve. And like I said, this green line is called the integration line. And of course, if you've ever taken any calculus and you know that how do you find the area under a curve, you integrate that function. And so that's actually what they're doing, is this line's going along and it's going up every time it finds any area under the curve. And so when it gets to this peak, it'll be like, oh, okay, here's some area, and it goes, and then it's done with that peak, and then it stays flat, and then it tells you that. So again, like I said, you can technically measure the height of the green line for this peak and compare it to it's all relative, so it may not mean anything. If I were to measure this, it might be like 1 inch, 1.5 inches. And so if it's about 1 to 1.5 or 2 to 3 or 4 to 6 in this case, so you have to relate it to what you already know about the molecule. But if you don't see any numbers, but you do see these green lines, you can literally take a ruler and measure them and compare them. All right, here's another example. So you can see we have 2 peaks, and that's good because we have 2 types of hydrogen. They're slightly different. They're both methyl groups, but they're in slightly different neighborhoods or regions. And let's see, which one do you think is which? So one of the hydrogens is directly attached to a C double bond O. The other carbon is directly attached to an O. And if you might go back and pause this and go back and look at some of the other slides where the regions are, but if it's directly attached to the O, that's going to be a little bit further de-shielded than this one is. So this one will be the further to the left, and this one will be the one further to the right, because it's a little more shielded because it's still attached to a carbon. Even though the carbon's attached to an oxygen, the carbon is a little less withdrawing than an oxygen is. Now notice that these peaks are almost identical in size. The integration here, if you measure the integration here and here, you'll find that they're going to be equal to each other, and that makes sense because we have a ratio of 3:3. So you probably see 1:1, or you might see 3:3 if you don't know what the compound is. All right, so again, this is just repeating. This is kind of, if you were reading my slides without me, this would be describing what I just said. So again, the hydrogens on the carbon next to the carbonyl will be slightly more shielded. The one attached to the oxygen will be further to the left. And after a while, you start to get used to, you know, if the hydrogen is attached to a carbon attached to an oxygen, it tends to be right around 4, something like that. And like I said, I have forms that when we get into lab, we'll be looking at them, and you can sort of identify what kind of hydrogens you would expect at certain locations on the axis, and that's really helpful. And again, since both types of hydrogen are an equal number, the area under the peaks are equal, and so the ratio is 1:1. All right, here's one more example, and this one I do want to point out. I've already given you the arrows here. So here's a hydrogen directly attached to a C double bond O. So this time it's not on a carbon attached to a C double bond O, but the hydrogen itself is attached to a carbon. So it's highly de-shielding. And so you can see here that actually gives rise to a peak here close to 9, somewhere between 8 and 9. And then notice that these three, you may not realize it at first, but all 9 of these hydrogen are identical to each other because they're all methyl groups attached to the same carbon. So these all 3 will give rise to only one peak. And so that happens to be this peak. And obviously they're all sp3 hybrided, and they're pretty far away from this C double bond O. So they're way down here around 1. They're pretty shielded. And so that should make sense. This one's much further to the left, and these are much further to the right. And then the same thing about the ratio. Now, here they're doing it a little bit differently, and they're telling you, here's the integration. In other words, they measured the amount of area under the curve. And so again, it's sort of, you're just looking at the ratio. This number doesn't tell you much, but if you take the bigger one divided by the smaller one, which I did down here, 155.4 divided by 17.3 gives me 9. You can take the bigger one divided, well, you divide them both by the smaller number, and obviously if you divide the smaller number by itself, you get 1. So that's a 1:9 ratio. They may not come out exactly perfect, but they should come out close to a whole number. So this means that the area under this peak is equal to 9, and the area under this peak is equal to 1. So that's a 1:9 ratio, which is what we expect. Here's another example. This one, you can see that I've already circled the hydrogen. There's 3 different types of hydrogen, 3 different signals, and notice that these 3 and these 3 will be the same. So we have 6 hydrogen here, we have 1 here, and we have 1 here. Hopefully by now you can see that these 6 right here are the least shielded because they're attached to a carbon. Now the second carbon is attached to O, so it's a little further down than 1, but it's still not very far. So this is the 6 carbons here in the middle. And then notice that this hydrogen itself is directly attached to an O. So that is pretty de-shielding. So that moves us down here to about a 2. Actually, it's interesting, a hydrogen attached to an oxygen actually can show up in a pretty big range. So it's sometimes that one's really hard to tell. But it's pretty obvious here because it's got to be one of these two small lines. And then this hydrogen, which is attached to a triple bond, and a triple bond will be more deshielding, is also one of these two. Now, to tell you the honest truth, I would not be able to say for sure that this one is to the right and this one's to the left, because it's a little bit of arbitrariness, and they're both very, very close. One's at 2.3, one's at 2.4, so it would be really hard to tell, but I think you can say as much as these two hydrogen are represented by these two lines. It will be really hard to say which one is a little bit more, but clearly the one with 6 here is the ones in the middle, and they are the least deshielded, or the most shielded. That's kind of gets crazy sometimes when you say the most deshielded. Actually, they're the most shielded, so they're the furthest to the right. And then looking at the integration again, I kind of did the math over here. I took all of them divided by the smallest, which is 7.5. So if you take 45.8 divided by 7.5, you get 6, which is what we were expecting. And then 7.7 divided by 7.5 has got an extra little dot there, but that you get it. It's approximately 1, and this one again is close to 1. So there's just a little bit of machine error or whatever. So, but they're very close to 6 to 1 to 1, which is what we expect. And then here's one more example again, and I've already labeled it for you, so we can see that there's 4 peaks. Now, I wouldn't go straight to the numbers and figure out the numbers. And keep in mind that in this case, we know what the compound is, so we're just identifying which peak is which. And that is helpful to go ahead and divide and find out the numbers, and that might help us figure out which peak is due to which, but not always. So you do want to also keep in mind the how far to the left they are and how deshielded they are. So we can see here that we have 1 hydrogen attached to an O. In this case, these are equivalent. So these 6 hydrogen are both attached to a carbon. So they're going to likely be the least deshielded, or the most shielded. This one's pretty shielded too, because it's a sp2 hybrid, and that's 2 there. And it's going to be similar to these because it's attached to carbons. It might be slightly further left because it's attached to directly to the C double bond O, although these are attached to the C, attached to the O. So, but I'd say this one being between both of these carbons might be a little further left. But when we look at it, we'll see that it'll make sense. And then here's 3 way over here on the right, which it's going to be similar. These two are going to be similar, but again, the one labeled C is going to be maybe a little further left because of the being between both of these, whereas this one's just next to the C double bond O. So if we look at that, and again, if we do the math, we can see that peak A is 6, so that makes sense. That's the most shielded, so that's that peak. B has 3 carbon, and if we take 37.7 divided by 12.5, we get 3. So that is 3 hydrogen there. And then C is 2 hydrogen and 1 hydrogen. Like I said, the hydrogen attached to an O sometimes is hard to place. It might, you can see here, the last one it was right around 2, and here it's closer to 4, so it kind of can be a little bit harder to identify, but it has to be, the one here at D has to be the OH, because it's the integration gives you 1 hydrogen. And then this makes sense that C is a little bit further left than B, since C is between both of these, a little bit more withdrawing, and then it makes sense that A with 6 is the least deshielded, or the most shielded. So it's the furthest to the right.